Welcome back to the deep dive. Okay, today we're dispensing with the usual pleasantries because, frankly, we have a job to do.
Hmm.
I want you to shift gears mentally. For the next hour or so, you are not just a listener.
Not at all.
I want you to role play with us. You have just been appointed as the senior technical strategy consultant at a Tier 1 automotive engineering firm. You've got the corner office, you've got that panoramic view of the test track.
And you have a very, very expensive espresso machine that you haven't quite figured out how to use yet.
You haven't had the time.
And more importantly, you have a headache. A massive strategic headache.
Exactly. Because the board of directors just dropped a mandate on your desk with a deadline of, well, yesterday.
Of course.
The subject line is 2024-2026 Global Next Generation In-Vehicle Communication Technology Strategy Report.
Sounds a little dry, doesn't it? But in our world, that is a panic-inducing email.
Oh, yeah.
That is the kind of email that absolutely cancels vacation.
They don't want a summary from you. They don't want a literature review. They want a roadmap. They want to know how we take a car, which used to be, let's be honest, a bunch of metal, gears, gasoline, and maybe a radio,
Right.
and turn it into a data center on wheels. And they want to do it without the car, crashing, overheating, or costing more than a small house.
And that is the crux of the issue,
Right.
We're trying to turn this mechanical beast into a digital organism.
Mm-hmm.
But the nervous system of that organism, the actual wiring, the copper, the communication protocols we use to move data around, it's failing.
It's failing.
It's old, it's heavy, and as we're going to discuss in excruciating detail today, it is literally hitting the laws of physics.
So that is our mission. We're going to write that report for you right here, right now. We're going to break down the strategy to build the car of 2026.
Yeah.
But we aren't just going to throw tech jargon at the wall. We need a structure. If we're going to deliver a strategic masterpiece, we need a framework that holds up under scrutiny.
Right. If we're playing the role of high-end consultants, we need a high-end framework. So we're going to use the top-down approach, and specifically, we're going to use the MECE principle.
MECE. Let's
Yep.
spell that out. MECE. Mutually exclusive, collectively exhaustive.
It's the gold standard for strategy, often associated with McKinsey. It means we're going to categorize the car's communication network into distinct layers.
Okay.
Those layers must be mutually exclusive, meaning they don't overlap. You don't want to solve the same problem twice in two different ways.
Efficiency is key here. Got it.
Exactly. But, and this is the other half, when you stack those layers together, they must be collectively exhaustive.
Meaning they cover everything.
Absolutely everything. No gaps, no magic happens here, boxes. We are going to map out the entire nervous system from the high-speed optical backbone all the way down to the wireless edge.
I like it. It keeps us honest. It prevents us from getting lost in the weeds before we see the whole forest.
Mhm.
We've got a massive stack of research here. Reports on optical Ethernet standards like IEEE 2.3 SISs, deep dives into the physics of CAN-XL, tech specs on Bluetooth Low Energy.
White papers on time-sensitive networking. All of it.
We're going to synthesize all of this into one cohesive narrative for you.
So let's start where any good report starts.
Mm-hmm.
The executive summary. The 30,000-foot view.
Right.
What is the fundamental shift happening here? Why are we even rewriting the rule book?
The core conflict seems to be this transition from function-defined vehicles to software-defined vehicles, or SDV.
Yeah.
We hear SDV as a buzzword constantly. It's in every marketing deck. But what does it actually mean for the guy, the person designing the wiring harness?
To understand the future, you have to look at the past. Historically, a car was function-defined. And this really reflects the organizational structure of the car companies themselves.
How so?
You had a braking department, you had a lighting department, you had a comfort department, deep, deep silos. So if the braking department wanted ABS, they bought a black box, an ECU, an electronic control unit from a supplier. Okay. They bolted it to the chassis and they ran wires to it. Then the lighting department wants automatic headlights. Great, add another black box, run more wires. You want power windows.
Another box.
Other box, it's additive. You just keep piling things on.
That's chaotic.
It's totally chaotic. And the result is a modern luxury car with, 150 different ECUs?
150?
And about 5 kilometers of copper wire. That wiring harness is often the third heaviest component in the entire vehicle.
The third heaviest?
It can weigh as much as 2 adult passengers. Imagine driving around with 2 mannequins made of solid copper in your back seat.
Right.
That is the efficiency penalty we are paying.
And that is completely unsustainable. especially when we're fighting for every single kilometer of range in an EV.
Need is the enemy.
Exactly.
Correct. So the shift to SDV isn't just about software. It's a physical architecture change. We are moving to central compute plus zonal control.
Okay, break that down.
Instead of 150 weak brains scattered around the car,
Hmm.
you have one or two superbrains high-performance computers, or HPCs.
Right, the central compute.
And then, in each corner of the car, you have a zone controller.
So let's use an analogy. We're moving from a village where everyone is just screaming at each other across the street.
To a structured corporation. Exactly. You have a headquarters, which is the central compute.
And you have regional managers.
A zone controllers. You got it.
That helps clarify it. So the regional manager, the zone controller, it doesn't care what the device is. It just manages everything in its physical area.
Precisely. The zone controller for the front left of the car manages the headlight, the front left tire sensor, the driver's door lock, the window motor.
All of it.
It aggregates all that data, packages it up, and sends it up to HQ via high-speed link.
Which simplifies the wiring dramatically.
Because you aren't running a separate wire from the headlight all the way back to the dashboard. You just run it to the local zone controller, which is right there.
Okay, but here's where the burning platform comes in. The why now. Why do we need to change the communication technology now? Why can't we just use the old copper cables to connect HQ to these regional managers?
Two reasons, and they are both completely non-negotiable. Data volume and physics.
Let's look at the volume first. I'm looking at the specs for the level 3 autonomous vehicle. We aren't just sending turn on the blinker signals anymore, are we?
No, that era is just gone. We're streaming uncompressed 4K video. A modern sensor suite might have 12 to 20 high-resolution cameras.
20 cameras.
Then you add LiDAR, which is generating millions of points per second, these huge point clouds. Then you add radar. We were seeing bandwidth requirements jumping from, say, 2.5 gigabits per second to 50 gigabits per second.
50.
And that's a conservative estimate for the 2026 timeframe.
So the pipe needs to be massive. But this is where you mentioned the laws of physics. The report references Shannon's limit. That sounds like a hard wall.
It is a hard wall. Claude Shannon, the father of information theory, he defined the theoretical maximum rate at which data can be transmitted over a channel that's subject to noise.
And our copper cables?
Specifically, twisted pairs are hitting this wall hard.
Break that down for me. What actually happens when we try to push 50 gigabits through a copper wire in a car?
You face massive insertion loss. Think of the wire as a hose.
Okay.
At low speeds, water flows freely.
Right.
But at high speeds, which are high frequencies in our world, the water starts to stick to the sides of the hose. The friction increases.
So the signal degrades.
By the time the signal gets from the trunk to the hood, it's gone. It's just dissipated as heat. The signal just dies before it gets to the other end.
And it's not just the cable itself, right? It's the environment. We aren't running this cable in some pristine laboratory.
Not even close. We're running it inside an electric vehicle.
Which is?
An electric vehicle is a nightmare environment for data. It's an electrical storm. You have an 800-volt high-voltage system powering the motors.
800 volts. That's serious power.
And it's not just sitting there. It's not DC power. The inverters are switching that current thousands of times a second to drive the AC motors. And that switching creates massive electromagnetic interference, or EMI.
It's broadcasting noise.
Just blasting it out.
So if I run my copper data cable next to that high voltage line...
Your data gets corrupted. It's like trying to whisper across a room while a jet engine is taking off next to you.
So the noise part of Shannon's equation just goes through the roof.
Completely.
And historically, how did we fix this with copper?
Shielding. Lots and lots of shielding. You wrap the copper in aluminum foil. Then you braid it with a metal mesh. Then you ground it.
Which makes the cable
thick, stiff, heavy, and very expensive.
And we're trying to make EVs lighter and cheaper, so copper is failing us on weight, on cost, and on signal integrity.
Plus, there's the reliability factor. We call this determinism.
Determinism.
If you're watching a movie and the car is driving itself and a camera sees a pedestrian, that data must reach the brain in microseconds. Not milliseconds, microseconds.
And why is that distinction so important?
It has to happen exactly when predicted, every single time. Because in standard networking, like your home Wi-Fi or your office, Ethernet packets are delivered on a best effort basis.
Right.
If a packet drops, Netflix buffers for a second, no big deal. If a packet drops in a car and the brakes don't engage,
catastrophic failure.
It's a catastrophic failure. We need fail operational reliability.
Okay, so the burning platform is crystal clear. Copper is too heavy, it's too susceptible to noise, and it's hitting its speed limit. We need a new strategy.
We do.
So, applying our MECE framework, we are dividing this report into 3 distinct layers to solve this.
Correct. We are building a layer cake. Layer 1 is the backbone. This is the high-speed highway connecting the brains.
Layer 2.
That's the nervous system, the deterministic control layer for real-time action.
And layer 3.
That's the edge, the wireless sensing layer for flexibility.
Okay, let's dive into layer 1, the backbone. The strategy report is pretty aggressive on this recommendation. For the multi-gigabit era, we're talking 2.5G to 50G and beyond. It dictates a hard switch from copper to optical Ethernet.
Specifically, the IE 802.3 SISI standard. This is a strategic pivot. This is the hill we are choosing to die on, so to speak.
Now, I have to play devil's advocate here because I know our client, the engineer listening to this, is skeptical. I can hear them rolling their eyes right now. Optical fiber in a car. Are you crazy?
Glass breaks, right. That's always the first thought.
Exactly. Cars vibrate, they slam into potholes, they get in crashes, they freeze in Alaska, and they bake in Arizona. Is putting glass wires in a car really a viable engineering decision?
And that is the most common misconception. It's one that holds a lot of companies back. But the optical fiber used in automotive, specifically OM3 glass fiber, is not the fragile stuff you make wine glasses out of.
It's not.
No, it's incredibly robust.
How robust are we talking?
It's designed to withstand vibrations of 10G or more. It handles temperature swings from -40 to 105 degrees Celsius. It has a bend radius that lets you route it through really tight spaces in the chassis.
It's flexible.
Very flexible. You can tie it in knot. I wouldn't recommend it for signal quality, but it won't snap.
So the durability concern is basically a myth.
It's a legacy myth. But durability aside, the real reason it's this strategic choice is EMI immunity.
Right.
Remember that 800-volt noise we talked about? The jet engine in the room?
It's the electrical storms.
Glass is a dielectric. It does not conduct electricity.
So
You could run an optical fiber directly through the middle of an electric motor, and the data wouldn't flicker. It is completely immune to electromagnetic interference.
which means no shielding.
Zero shielding. No grounding loops, no heavy metal braid. You save a massive amount of weight, and you eliminate the headache of trying to filter out noise. For the EMC engineers, the electromagnetic compatibility folks, this is like a religious experience.
Their biggest problem just vanishes.
Oof. Gone.
That sounds like a dream. But let's talk performance. I'm looking at a chart here comparing copper 802.3T versus optical 802.3Cs, and the latency numbers are, well, they're striking.
This is where the physics really separates the two. Let's look at the copper, 802.3. When you try to push 10 gigabits over copper in a noisy car, the signal degrades massively.
It's fuzzy.
It gets incredibly messy. So the chips on either end, the PHY chips, they have to do a lot of heavy math to reconstruct the signal.
Okay.
They use complex forward error correction, or FEC, and interleaving.
So basically, the chip is guessing what the signal was supposed to be.
It's a very educated guess. It's analyzing the noise, looking for patterns, and mathematically removing the static. But that math takes computation cycles. It takes time.
It adds latency.
It adds about 2 to 4 microseconds of latency to every single packet.
No, that sounds fast to a human. A microsecond is a millionth of a second.
To a human, it's instant. But in the world of autonomous driving synchronization, 4 microseconds is an eternity. It creates jitter. It makes it really hard to sync the left camera with the right camera perfectly.
Yeah. Look at optical.
Because the signal is clean, it's just light blinking on and off. The processing is incredibly simple. There is no noise to filter out.
So the latency is?
It's under 1 microsecond. And here's the paradox that engineers love. With optical 802.3 synestheses, the faster you transmit data, the lower the latency drops.
Wait, why is that? How does it get faster with more speed?
Because the bits are shorter. At 50 gigabits, the pulse of light is just shorter in duration than at 10 gigabits, so the system processes it faster. It actually gets more efficient at speed.
Whereas copper gets worse at speed.
Exactly. Copper gets worse, optical gets better.
So it's cleaner, it's lighter, and it's faster. But we have to address the implementation side of our report. How do we actually build this? The report highlights a specific technology here, KBPOF and their KD7251 transceiver. What makes this chip so significant?
This chip is a great example of the integration we need to make this viable. In the past, optical systems were clunky.
Right.
You needed a laser diode. Then you needed a lens to focus it. Then you needed a detector. Then you needed a processor. It was a science experiment.
Yeah, not something you want to put on a mass production assembly line.
Exactly. KDPOF managed to integrate the electronics, the photonics, and the optics into a single package. It looks just like a standard chip you'd solder onto a board.
The laser is built in.
The laser and the driver are all built in.
That simplifies the supply chain immensely. But what about cost? We always hear fiber is expensive. I can't afford fiber in a Corolla.
And this is where you have to put on your consultant hat and look at TCO, total cost of ownership.
Okay.
If you just look at the chip price, sure, the optical chip might be $1 or $2 more than a copper chip right now.
But that's not the whole story.
Not at all. You have to subtract the cost of the cable. Copper cable for 10G is expensive. Optical fiber's cheap. It's just plastic and glass.
Right.
You subtract the connectors. Copper connectors for high speed are these gold-plated engineering marvels. Optical connectors are simpler. You subtract all that heavy shielding. And you subtract the complex noise cancellation circuits on the PCB.
So when you look at the whole system,
The optical system actually comes out cheaper at the system level for anything above 10 gigabits per second.
plus there's the future-proof argument.
That's a huge point. If you install OM3 glass fiber today for a 10 gigabit link, that same piece of glass
The same physical fiber.
can support 50 gigabits or even 100 gigabits in the future.
You don't have to rip the car apart.
You just upgrade the transceivers at the ends. With copper, if you want to go faster, you almost always have to rip out the cable and put in a thicker, higher grade one.
And that is a massive selling point for a car manufacturer. You do not want to redesign the wiring harness, which is the most complex part of the assembly every 2 years.
Absolutely not. So for the backbone connecting the central computer to the zone controllers or aggregating massive camera feeds, optical is the clear winner. It's the only strategic choice.
Okay, that covers the high-speed backbone. Now let's move down a layer in our MECE framework, layer 2, the nervous system.
This is where things get really interesting for the engineers who've been in the industry for a while, because we're talking about CAN.
Controller area network. It's been around since the 80s. I think my toaster might use CAN.
It might,
If optical is so great, why don't we just use optical for everything? Why keep this old tech?
because optical is like a bullet train. It's fantastic for going long distances very fast with lots of people.
What?
You don't take a bullet train to go to the grocery store.
Meaning?
For this middle layer connecting things like door locks, windows, seat motors, the sunroof, even some parts of the steering optical is just overkill.
Mm.
It's too power hungry and it's too expensive per port to put on a simple window switch.
But the old CAN bus classic CAN is way too slow. It tops out at 1 megabit.
Right. And even CAN-FD, the flexible data rate version that came out a few years ago, that only gets you to about 5 or maybe 8 megabits and a payload of 64 bytes.
So we have a gap. Optical is up at 10 gigabits. CAN-FD is down at 5 megabits. There's this massive wasteland in between.
And our report says this gap is filled by CAN-XL, extra large.
I love the naming convention. CAN-XL. What does it actually deliver?
CAN-XL is the bridge. It completely redefines what CAN can do. First, look at the payload. CAN-FD maxed out at 64 bytes of data per message. CAN-XL goes up to 2048 bytes.
That is a massive jump. That's not just a little tweak. That's a different class of communication entirely.
It's significant because 2048 bytes is large enough to hold a full Ethernet frame.
Wait, explain that. Why would we want to put Ethernet inside of a CAN message?
It allows for something called protocol tunneling. In the SDV world, everything speaks IP Internet Protocol. Your software wants to send an IP packet to the window motor.
Okay.
With CAN-XL, you can take that Ethernet frame, wrap it inside a CAN-XL frame, and send it over the cheap twisted pair of wires.
So CAN-XL acts like a last-mile delivery service for the Ethernet backbone.
Precisely. You get the benefits of IP networking like end-to-end addressing without the cost of putting an Ethernet switch port at every single sensor in the car. It unifies the whole software stack.
But how does it achieve the speed? The report mentions 20 megabits per second. How do you get that kind of speed on the old two-wire system?
This is a brilliant piece of electrical engineering. To understand it, you have to understand how classic CAN works. It uses what's called open collector logic.
Break that down for us.
Okay, imagine a signal line is held up by a spring, which is a resistor to 5 volts. That's your recessive state, or a logical 1.
Right.
To send a 0, or a dominant state, a transistor actively pulls the line down to ground.
So pulling it down is fast because you're using power, but letting it go back up.
Relies on that spring. It relies on the resistor to pull the voltage back up. It's passive. And that passive return is slow. It limits how fast you can toggle the bits. The capacitance of the cable fights against that resistor.
Okay, I think I follow. It's like pushing a swing. You can push it forward really fast, but you have to wait for gravity to bring it back.
That's a perfect analogy.
Yeah.
CAN-XL changes the game. In the fast data phase, it switches to push-pull logic.
Push-pull.
It actively pushes the voltage up for a 1, and it actively pulls it down for a 0.
So you're pushing the swing in both directions. You aren't waiting for gravity anymore.
Exactly.
Hmm.
And that allows you to drive the signal much, much faster, up to 20 megabits.
But doesn't that break the old rules of CAN? I thought the whole point of CAN was that if two nodes talk at the same time, the dominant one, the 0, wins. That arbitration relies on the open collector method.
You are spot on. If you use push-pull during arbitration, and one node pushed the voltage UP while another pulled it down, you'd have a short circuit.
You blow the chips.
You would. So how does CAN-XL handle that?
Yeah.
It splits the message into 2 phases. The arbitration phase, the header, still uses the old slow, polite, open collector method. So the nodes figure out who gets to talk using the old rules. But once the channel is secured and one node wins,
It switches gears.
it switches to turbo mode, push-pull blasts the 2048 bytes of data at 20 megabits, and then switches back to the slow, safe mode at the end.
That is incredibly clever. It maintains backward compatibility for the important part, the arbitration, but gets the speed for the payload.
It's engineering elegance, really.
Now, I see a note here about SIC transceivers. SIC, signal improvement capability. Why is this mentioned as a requirement?
Right. So when you send data at 20 megabits over a wire, you start treating that wire as a transmission line, and the signal can bounce off the ends of the wires, creating ringing.
Like an echo in a large empty room.
Exactly. If that echo is too loud, the receiver can't understand the next bit of speech. In the old days of high-speed CAN, you needed a perfect linear line. No branches, no long stubs.
Which made the wiring harnesses a nightmare to design.
A total nightmare because you had to snake the main line into every door and then back out again.
Which uses more wire and adds weight.
SAC transceivers actively suppress that ringing. They basically dampen the echo.
And why does that matter for the wiring harness design?
It allows engineers to be a little bit sloppy with their topology in a good way. With SSC, you can have longer stubs, these branches off the main line. You can run a 5-meter branch into a door without disrupting the main bus.
So it makes the physical layout of the car much, much easier to deal with.
A lot easier.
So CAN-XL gives us speed, data size, and topology flexibility. Now, within this nervous system layer, we also have to talk about control, not just moving data, but controlling when it arrives. This brings us to TSN, time-sensitive networking, and SDN, software-defined networking.
This is really the brain of the nervous system.
Yeah.
In a software-defined vehicle, workloads are dynamic.
Right.
Maybe you download a new app to the car.
Yeah.
Maybe an autonomous sensor fails, and you need to reroute data. The network has to be able to adapt.
So TSN provides the rules.
TSN provides a hardware guarantee. It's a whole suite of standards.
Yeah.
But the most important one is 802.1AS for time synchronization. It gets every clock in the car, the camera, the central computer, the braking ECU synchronized to within a microsecond. Everyone is looking at the exact same stopwatch.
Why is that so critical?
Data fusion. If the camera sees an obstacle at time t and the LiDAR sees it at time t, the computer needs to know those are the same moment in time.
Of course.
If the clocks are off by even a few milliseconds, the computer might think the obstacle is moving when it's actually standing still.
That makes perfect sense. And what about the other one? 802.1 QAFIV.
That is traffic shaping. It makes sure the important data gets to cut in line. Imagine a highway. 802.1 QAV-EV creates an emergency lane that is always open for the ambulance, which is the brake signal, no matter how jammed the other lanes are with regular traffic.
Like Spotify and map updates.
Exactly.
So TSN is the traffic cop enforcing the laws of the road. Then what is SDN?
SDN is the city planner. SDN decouples the control plane from the data plane.
Okay, let's unpack that. That sounds like a bit of IT jargon. Control plane versus data plane.
Think of a network switch. The data plane is the muzzle. It just moves packets from port 1 to port 2.
Yeah.
The control plane is the brain. It decides which packets go where.
And in the old days?
In the old days,
Yeah.
that brain was hard-coded into the firmware of every single switch. If you wanted to change the traffic flow, you had to reflash the firmware of every switch in the car. It was static.
Which is a nightmare if you want to update the car over the air.
It's impossible.
Yeah.
But with SDN, you have a central controller, a piece of software running on the main computer that sees the whole network map.
Right.
It calculates the best routes and schedules, and then it pushes that configuration down to the switches. The switches become dumb, obedient muscles. The intelligence is centralized.
The report has a great example of why this matters, road noise cancellation, or RNC. Walk us through that because it really highlights the need for both speed and flexibility.
This is a perfect use case. Premium cars today, they want to be silent.
Yeah.
So to cancel road noise, The hum of the tires on the pavement. You have accelerometers and microphones listening to the suspension.
Yep.
They send that vibration data to a processor. The processor creates an anti-noise wave, an inverted wave, and sends it to the speakers to cancel out the hum.
So it's active noise-canceling headphones, but for the whole car.
Exactly. But here is the physics problem. Sound travels 1 meter in about 3 milliseconds.
That's fast.
It's very fast. If your network latency, the time it takes for the mic signal to get to the processor and then back to the speaker, is slower than 3 milliseconds, the anti-noise arrives too late.
And if it arrives late?
It's out of phase. So instead of canceling the noise, you actually amplify it. You make the car louder.
Ouch! So the network performance literally determines if the feature works at all.
It's make or break. Now, imagine an engineer improves the RNC algorithm a year after you bought the car. She says, I can do better cancellation, but now I need the network latency to be 1.2 milliseconds, not 3.
Right.
In a traditional car, you'd say, sorry, can't do it. The wires are what they are.
But with SDN?
With SDN, the central controller calculates a new schedule. It says, okay, these microphone packets are now priority 1, map updates are now priority 5. It pushes the new config to the switches. The network reoptimizes itself. Boom.
The car is updated.
The car is updated. The hardware didn't change, but the capability did. That's the definition of software-defined.
It allows the car to improve with age.
Precisely.
All right, we've done the backbone with optical and the nervous system with CAN, GaN, electrical, and TSN. Let's go to the final layer, the edge.
This is the wireless layer.
And the strategy here is interesting. It says, remove the last meter. And we're talking about Bluetooth low energy, BLE, specifically automotive grade BLE.
Now, I know you're thinking, wireless. In a car. Isn't that unsafe? Can't someone hack it?
I was thinking exactly that. I thought wires were always better for reliability.
And for safety-critical things like steering or braking, yes, absolutely keep the wire. We are not proposing wireless brakes.
Okay, good.
But for non-safety things, TPMS, ambient lighting, seat adjustments, door handles, wires are heavy.
How heavy?
Well, every sensor you wire up needs 2 copper strands and a connector. A door harness is this thick, complex snake of cables. If you can remove those wires, you save kilograms of weight and you simplify the assembly process dramatically.
The report highlights the Renesas DA14533 chip. Why this specific chip? Why not just any old Bluetooth chip?
It's a significant piece of silicon because it's the first automotive-grade BLE chip from a major player like Renesas. But the key spec here is power. It has a hibernation current of less than 550 nanoamps.
Nanoamps, that's billionths of an amp.
Correct. It basically runs on the smell of an electron.
I love that. But practically, what does that allow us to do?
It means you can put this chip in a tire pressure sensor, seal it inside the tire with a little coin cell battery, and it will run for 5 to 7 years.
Without being recharged.
You don't need to run a power wire to it. You don't need to generate power from the rotation of the wheel. It just sips energy.
Let's talk about that TPMS use case, the tire pressure monitoring system. We've had TPMS for years. Why switch from the old radio frequency way to Bluetooth?
The old way, using that proprietary 433 megahertz RF, was a one-way shout. The tire just screamed, I'm at 32 psi over and over and hoped the car heard it. It was dumb. It couldn't receive instructions.
And Bluetooth?
Bluetooth is two-way. The car can wake up the sensor, it can ask for specific data, it can update the sensor's firmware over the air, and crucially, because it's standard Bluetooth,
So my phone can talk to it.
your phone can talk to it.
So I can walk up to my car, pull out my phone, and check the tire pressure without even turning the car on.
Exactly. Or a mechanic can diagnose it with a standard tablet. It integrates the car into the consumer electronics ecosystem we all live in.
Now, there's a detail in the report about this chip that sounds oddly biological. It says, wettable flanks.
Aha. Yes. It sounds like something from a nature documentary, doesn't it? But it's purely mechanical, and it is absolutely vital for our engineer listener.
Explain it to me. Why do the flanks need to be wettable?
Okay, so a standard consumer chip, like the one in your Fitbit, often has its connection pins hidden underneath the package. It's called a QFN package. You solder it to the board, but you can't see the connection.
Right, it's underneath.
Which is fine for a Fitbit, but for a car. In automotive manufacturing, reliability is everything. You need to verify every single solder joint. You cannot verify what you cannot see.
Because if that joint cracks...
The sensor fails.
So how do wettable flanks fix this?
Wettable flanks means the side of the chip has this little exposed metal groove where the solder flows up the side when you heat it. It creates a visible fillet of solder.
So the solder connection is visible from the side.
Right. It allows a machine an AOI, automatic optical inspection camera, to look at the side of the chip and say, yes, that is a good, solid connection. If you don't have wettable flanks, you have to use X-ray inspection, which is slow and very expensive.
So consumer chips don't have this?
But automotive chips must have it.
That is the kind of detail that separates a generic report from a real technical strategy. It's not just about the protocol, it's about, can you actually build this thing reliably in a factory?
Exactly. Strategy is execution.
This leads us perfectly into Section 5, engineering challenges and implementation strategy. We have the tech stack. How do we actually build this thing without going crazy?
The biggest challenge identified is the mixed network migration. You are never building a car completely from scratch. You have legacy parts. You have parts from the 2023 model that you want to carry over to save cost.
The legacy problem. We can't just throw away all the old sensors.
And specifically with CAN-XL, remember CAN-XL uses that new protocol, that new fast data phase. If you have an old classic CAN ECU connected to the same wire and it sees a CAN-XL message,
What happens?
it freaks out. It sees the fast data phase and thinks, this is noise, this is an error.
Uh-oh.
And in the CAN protocol, when a node sees an error, it is programmed to scream error and pull the bus voltage down to kill the message.
It's a suicide pact.
It's basically a suicide pact. It's called an error frame. The old node thinks it's saving the network by destroying what it perceives as a bad message.
So one old sensor can take down the whole network.
It can. So the strategy requires zone separation. You must use bridges. You physically isolate the classic CAN nodes on their own slow bus, and then a bridge translates their data onto the fast CAN-XL network.
So you can't mix them on the same wire?
Not unless the old nodes are CAN-XL tolerant, meaning they're smart enough to just shut up and ignore messages they don't understand.
Good to know. Don't mix the generations without a babysitter. What about verification? Shift left is the buzzword here.
Shift left just means testing earlier in the development timeline. In the old days, you'd wait for the hardware prototype to arrive, hook it all up on a bench, and start debugging.
But with SDV, the software is huge. If you wait for hardware, you're already late.
You're dead in the water. The strategy calls for virtual ECUs, VECU. You simulate the network chips on the cloud using things like AWS RM instances. You achieve bit parity, meaning the simulation behaves exactly the same as the real wire, bit for bit.
So you're testing your SDN configurations, your security keys, your routing logic.
All in the cloud, months before the physical silicon arrives at the factory. You find the bugs when they're cheap to fix, not when you have 10,000 cars sitting on the assembly line.
And finally, security. Cybersecurity by design.
Well, we connected the car to the internet, and we filled it with high-voltage interference. It's a dangerous mix.
The report lists a few acronyms we need to know here.
I-
AMSIC and SECOC.
MCSEC is for the Ethernet backbone. It encrypts the data at the hardware level, right on the wire. So even if someone could tap the optical fiber, which is hard, by the way, they wouldn't be able to read the data, it protects a highway.
And SECOC.
Secure onboard communication. This is for the CAN layer. It adds a digital signature to important messages. It's like a wax seal on an old letter. When the brakes get a command to stop, they check the seal. If it's broken or fake, they ignore the command. This prevents a hacker from plugging a laptop into, say, the headlight port and sending fake brake commands.
And post-quantum cryptography. Are we really worrying about quantum computers hacking cars already?
We have to. Cars stay on the road for 15 or 20 years. By 2040, quantum computers might be real threats to our current encryption.
And hackers are.
They're already doing store now, decrypt later. They record encrypted traffic today, and they're just waiting for the computer that can crack it in 10 years.
That is terrifying.
So the strategy says we need hardware security modules, the HSMs, that are crypto-agile. We need to be able to update the lock algorithms over the air if the old locks get picked. We need to be able to change the keys to the castle remotely.
That is some serious forward thinking. Okay, let's wrap this up with the strategic roadmap and recommendations. What's the timeline for our consultant listener? What should you be doing?
Okay, 2024 to 2026. Phase 1 is standardization. Lock in IEE 802.3 CZens and CAN-XL now. Don't wait. You need to protect your CapEx, your capital expenditure. If you design with proprietary tech now, you'll be rewriting it in 3 years.
Okay, phase 2.
Optical adoption. For any vehicle starting production SOP in 2026 or later, especially premium EVs, optical Ethernet is mandatory for the backbone. It is the only elegant solution to the EV EMI problem.
And phase 3.
Automation. Get out of Excel for network scheduling.
I feel personally attacked. Spreadsheets are life.
We all love them, but you cannot manage thousands of signals in nanosecond timing in a spreadsheet. It's not possible. You need model-based workflows and agentic quality engineering. Let AI help you test the network.
And finally, the supply chain recommendation.
Stop buying components. Stop just buying a Bluetooth chip. Buy a pre-integrated platform and demand white box visibility from your suppliers. You need to see the source code of the software running on those chips. You are the system integrator. You need to own the stack. If you rely on a black box from a supplier, you can't fix bugs, and you certainly can't innovate.
So to summarize for our consultant listener, here is the executive summary of your final report. The car is becoming a data center.
Yep.
Copper is hitting the wall of physics.
Hard.
The solution is a MECE layered cake. Optical for the heavy lifting backbone. CAN XL and TSN for the precise deterministic nervous system. And automotive BLE for the flexible low-power edge.
And tying it all together is SDN software that allows that network to adapt and evolve over the life of the car.
It's a massive transformation. It's moving from building a machine to architecting an organism.
That's really what it is. It's a profound shift.
And that leads me to our final provocative thought. We talked about SDN allowing the network to heal itself, to reroute traffic if a line breaks, to update its own schedule if requirements change.
Right. Self-optimizing.
So, if the car can reconfigure its own nervous system in real time, if it can sense a fault and think its way around that fault, how far are we from the car being self-aware of its own health? Not just reporting a diagnostic code, but actively managing its own survival.
That is the ultimate question, isn't it? When the nervous system becomes plastic, you could call it neuroplasticity in silicon, the line between a smart machine and a living entity starts to get very, very blurry.
A thought to ponder as you write that report. Take this MECE framework, go back to your engineering teams, and start the transformation. The 2026 deadline is closer than it looks.
Good luck. You're going to need it.
Thanks for listening to The Deep Dive. We'll see you on the next one.